Hey, welcome to Computing Foundations. This is a channel for beginners who want to learn about computers, programming, and the math, science, and art behind this world-changing field. I'm Josh Kilpatrick, a retired software engineer. Today, we're continuing with the C programming language, and the topic of today is pointers. I'm really excited about this one because I think just now we're about to really scratch into the surface of some of the more powerful and interesting features of the C programming language that we're going to spend a lot of time working on as we move forward. So let's dive right in. Today our topic is pointers, and in order to understand pointers, we really need to get in our mind very clear what is computer memory, how does computer memory work, and how do we think about computer memory when we're inside of a program, when we're writing or thinking about a program. All right, so let's start with this photo. I drew this for you, so I actually had to practice to draw this. At the center of every computer is a centralized processing unit, a CPU. This is the actual part of the computer that knows how to run instructions and follow the program that you've written. The CPU is, probably one of the greatest achievements of the modern era of technology. A centralized processing unit has access to usually a large amount of memory, which we also call RAM. Stands for Random Access Memory. So the computer, the CPU, can directly access memory. And here I've demonstrated or represented the memory as though it's like a piece of paper or a table with a bunch of different lines. What I'm intending for each of these lines to represent is 1 byte of memory, 8 bits of memory. And the way memory works is each location in the memory has an address. It's just a numerical value that the CPU can use to reference that piece of data. So the CPU can reference 8 bits, 1 byte of data at a time by interacting with the memory. Now, memory should not be confused with long-term storage, or what is often called, kind of a slang, a hard drive. A hard drive is designed to store data long-term. Even when you turn your computer off, the hard drive continues to hold the data that you stored in it. And the CPU can access things on the hard drive, things like files and programs on the hard drive, but the way that happens is the data from the hard drive is read first into memory, and then the computer, the CPU, accesses the data through the memory. The interface between the hard drive and memory is much slower than the interface between the CPU and memory. So that is to say, data can be read and written from the hard drive and placed into memory at a speed of about 6 gigabits per second. That ends up being 750 megabytes per second of data that can move out of the hard drive into the memory or the other way. Okay, so as we were saying, the data can move into the hard drive or out of the hard drive at this rate, about 750 megabits per second. Compare that with the connection between the CPU and the memory, where we can get close to 25,000 megabits per second of data being moved back and forth between the two. That means the memory is about 30 times faster than reading from your hard drive. Now, you may have heard before that a lot of modern computers don't really have spinning disks, optical hard drives anymore. They now have something called solid-state drives, SSDs. But the principle is still the same. The insides of the hard drive work differently. On a solid state drive, we don't have a disk that's spinning and it's not using optical technology to store data. But it's still constrained by this connection, which is called a SATA, S-A-T-A. This stands for something like serial, I'm forgetting the name, the acronym here, but this connection is called a SATA connection. And it has a limit of how much data can move across. All right, so this is how we think about our computer being organized. The CPU has access to the RAM, which is very fast. And then through the RAM, we have access to the hard drive, which is much slower, but much larger. It can hold a lot more data than the memory can. All right, so when we're working inside of a program, the way that we're interacting with memory is we're creating variables. We've spent a lot of time discussing variables and the different types of variables. So take a look at this code segment that I've created for you and the corresponding memory. So if in a program I declare a variable called age of type int, the processor will randomly assign 4 bytes of memory, and it will store the value 45 into the 4 bytes of memory. And this section of memory, these 4 bytes, from address 003 to address 006, are now referred to in the program by the name age. So by creating a variable, I've just named a section of memory that I want to allow the program to access. We have no control over exactly which segment of memory the computer is going to assign. In fact, we'll see in our sample program, if we run a program several times consecutively, each time we run it, different areas of memory may be assigned. It's not fixed. It's just a random thing that the computer is deciding what memory is it going to give to you for your variable. Here I define a variable called initial. I set it to my first initial J, and I'm showing you here another example. A character is only 1 byte, so the computer reserves 1 byte, writes your value J into that byte, and now you can refer to that byte using the word initial. So this is the basics of computers. Now, there's an operator I want to teach you about called the address operator, and it is an ampersand. If you place an ampersand in front of a variable name, the operator, the ampersand operator, returns you the memory address of the variable. So in these two printf statements, what would print to the screen would be the address of age, which is 0003, and the address of the variable initial, which in my example is 0001. So we're printing to the screen not the value that is stored in the variable in memory, but the address that is represented by the variable. This address of memory is literally in the computer where the data is sitting. So we can access the addresses of our variables. So this is how variables get assigned into memory and how we can think about accessing the address of the variable. So now, what is a pointer? What is a pointer? A pointer is a type of variable. Whenever I put an asterisk after the type name of a variable, I'm telling the compiler, I want to define a variable that is a pointer to an integer. A pointer to an integer. So what do I mean by a pointer? What a pointer is designed to hold is precisely the address of a variable. So here I assign to the integer pointer the address of the variable age. This is what a pointer is made to hold. It doesn't hold an integer, it holds an address of an integer. Here I define a second pointer of type char. it is pointed to the address of initial. So now this variable will literally have the number 0003. It's an address. This variable, the PTR pointer to variable, will have 0001. So pointers are simply variables that instead of pointing to a value that has been stored in memory, instead of holding a value that has been stored in memory, they hold a memory address. So if I were to run this code right here, I would print out, as we said earlier, 0003 for the age variable, and oh, sorry, I've misspoken. I've done something unique here, and this is the second aspect of pointers that I want to describe to you. If I have a pointer already, so I've already defined a pointer here. If I put an asterisk in front of this pointer when I refer to it in the program, I'm telling the compiler, I don't want to access the address stored in the pointer. I want you to follow that address to whatever it points to in memory and give me the value that is stored in memory. So when I say asterisk pointer 1, I'm saying go to the address that is stored in pointer 1. The address in pointer 1 is the age variable. The address is 0003. And when I put the asterisk there, I'm saying go to this address and tell me what is inside of the address. So at this address, we have an integer, 45, and this will now evaluate to 45, and this printf statement will print to the screen 45. Here, we print the initial character pointed at pointer 2. So the important thing to understand here is to declare a pointer, I use a type, a variable type, followed by an asterisk, and then I give it a name. This is a name of a variable pointer to an integer. To now access what is pointed to, the memory that is pointed to, I put an asterisk in front of the name of the pointer. So let's continue. I think this will get a little more clear as we continue. Why in the world do we want to do this? Is the question. Why are we defining a variable that holds a memory address if all we really want to do is access what is stored at that memory address? Why do we do it? So one reason we do it is related to functions. And we're going to take a step back and discuss something about functions that we did not explicitly discuss in our video on functions. So let's take a look at this function that I have defined. And after we've discussed the function, we will discuss this little memory drawing that I have here. So I'm going to cover that drawing up so it doesn't distract you. So in this definition, you should be familiar with this now from our video on functions. I define a function called increase by 1. I declare that the function will return an integer and that it will receive a single parameter, which is an integer called value. And here I say value equals value plus 1, increasing value by 1, and then I return value. So we will end up increasing whatever variable you pass in by 1 and returning that number. Now, take a look at what actually is happening in memory, something that I haven't told you before yet. When you define a function like this and you enter into the function, the computer reserves an area of memory for the function that will store all of the function's variables and all of the function's parameters. In this function, we don't define any new variable, but we do define a parameter and a return value. So what actually happens inside the computer is memory is reserved for the function, and an area of memory will be reserved, and the value passed in, which I'm calling in here, whatever value gets passed in, is stored in memory in a special area reserved for this integer parameter. And we can refer to it in the function using the name val. Now, we also reserve an area of memory that will be used for the return value. Whatever value I return will also get stored in memory, and when I exit the function, this piece of memory is available. It gets returned, the value in this piece of memory gets returned by the function, and we can do whatever we want with it. But as soon as the function finishes, all of this memory gets thrown away. It's no longer useful. The computer just reserved it for the moment that you entered the function, and then when you leave the function, it's no longer accessible. This memory is thrown away after we exit the function. It was memory especially reserved just for this function. So let's take a look at this imaginary piece of code that I might have stored, that I might be calling inside of my main function. So inside my main function, I create a variable called val, and then I call increase by 1. Now what happens when I call increase by 1 is, let's think about the memory here that exists in main. So I've declared an integer called val, and let's just imagine it's sitting right here in memory. I've started to break away from my norm. Really, an integer is 4 bytes that are reserved in memory. I'm just pretending like it fits into 1 byte just to make it a little easier to draw these diagrams, so don't let that confuse you. So here I'm imagining that I'm pointing to an integer, that I have an integer stored in memory, and its value is 10. So I have an integer stored in memory, value equals 10. I call increase by 1. Now what happens when I enter increase by 1 is this value in memory gets copied into a special new place in memory reserved for the function. And so 10 gets placed here. The function runs, I increment val, so I increment this memory to 11, then I return the value 11 from the function. The return value gets copied into memory here. And then all of this memory gets thrown away. And when I exit this function, and I'm back at this next line of the program, the original variable val that was defined in the scope of the main function has never been touched. I never referenced that memory in the function. I just copied from here into the function's memory, the function ran, and I exited. So if we were to print val at this section of the main function, the value that would get printed out would be 10. The val variable in this scope, in the main function scope, has never been altered. Now let's look at my next statement. What if I said val equals increase by val? Increase by 1 and pass in val. So now the valuable variable that we've never touched is going to get copied back into a special place in memory just for this function to run. The function will increment it to 11 and it will return 11. And here I use an assignment that says whatever this function returned, copy it into the val variable that is in the scope of the main function. So 11 gets copied from the memory of the function into the memory area of the main function. So this gets copied and gets turned to 11 because 11 is copied from here to here. And now when I print out the value of the variable, I will get 11. So what's the important lesson here in this example? When you define a function the way that we learned to define them in our video on functions, you are creating a function that has parameters that are, as we say in the computer programming field, passed by value. It means the value of the arguments are available to the function, but you're not actually giving the person access to the main memory that was in the main program, in the main function. You are just copying these values into special memory that the function can use. And then when the function's done, that memory is gone. So the only way to have a value come out of a function and be available to you back in your main program is to do an assignment like this. But this can have some disadvantages because I can only return one value from the function. What if I want to have several different values coming out of the function? Okay, this is where pointers come in. So let me show you another example, another way that I could have defined the increase by 1 function. So again, I'm still going to return an integer, but now I'm going to define the parameter not as an integer, but as an integer pointer, a pointer to an integer. Then inside the function, I'm going to dereference the pointer. So I'm accessing the value that is stored at this memory, and I'm going to increment the value stored at the memory address by 1, and then I'm going to return the value stored in the memory from the function. All right, so what is going to happen here is that when the program calls this function, we're going to pass the address of the value variable. The address of the value variable is 0001. We will pass the address into the special memory location allocated for the function. But then we're immediately going to dereference that memory address. We're going to say, hey, go look up this memory address, it's over here, and tell me what value is stored in that memory address. Then we increment it by 1, and we reassign 11 into the actual memory, and then we return 11. So let's look at what would happen if I had used this new function in a main program. So here again, I create a variable that is local to the main function. It's in the scope of the main function. I set it to 10. The memory is going to look like this. Then I call increase by 1, and I have to get the address of the local variable because this increase by 1 function requires that I pass in a pointer. It requires that I pass in an address. It's not asking me to pass in an integer value. It's asking me to pass in a pointer, an address to an integer value. So I get the address of this local variable and pass it in. Now, if I were to call printf after calling increase by 1, the actual memory referred to by val has been changed by the function. So I'm actually going to print out 11. Now, what happens if I call it this way? If I say val equals increase by 1? Well, the address of val gets passed into the function and stored in the function's local memory area. Then we run the code here, which will increase this local memory area to 12 at this point. It was 11 when I called the function, now it's 12. And 12 will be written here. So as soon as this function exits, the value of the val variable is going to be 12. But then I assign the value 12 back into the value variable. And so it's still just equal to 12, but it's equal to 12 now because I assigned the return value back in. So now if I print out val, I'm going to get 12. So this is the basics of how pointers work. And as we move forward in our programming journey, we're going to make a lot of use of these powerful pointers. They allow us to do some really fancy, interesting things by directly accessing memory inside of a function, instead of always just passing by value. Now, it's very common to pass by value in functions because it's often that we don't want the function to change anything about the parameters that were passed into the function. We just want the function to do some operation and return a value. We don't want it to mess with any of the memory in the main program. But other times, we in fact do want the function to mess with the main memory. And we'll see many, many uses of why this is so powerful and important as we continue our journey. But today, all we've learned is how to get the address of a variable and how to create a pointer variable which stores an address. We also learned how to dereference a pointer, so we can take an address that's stored on a pointer and find out what is the value stored in the memory to which this pointer points. It's a lot of circular talk, but if you just try to keep some of these visuals that I provided for you about the memory in mind, I think you'll be able to slowly wrap your head around how these pointers function. So as always, there's a wonderful coding sample ready for you in program number 9 called Pointers. Take a look at that program. Feel free to mess around with it, change things, break it, see what happens. But at the end of studying this program, you should have a little better of an understanding of how these pointers function and how we can use them to define a function that will actually alter the memory of the main program. Thanks for listening to this video, and we look forward to seeing you in the next one. Take care.